At takeoff and landing, we designed the aircraft to be 10 times quieter than a helicopter. And during cruise flight, 2,000 feet above cities, we designed the aircraft to be 100 times quieter than a helicopter to be the lowest noise signature possible.
We believe that noise will largely define the success or failure of this industry. To be successful, we have to deliver customers as close to their destination as possible. This means regular flights in and out of built-up areas, which only works if the aircraft is really quiet. A few months ago, we shared a video of our aircraft taking off behind me. Today, we wanted to give another demonstration of just how quiet our aircraft is. This is a calibrated decimal meter, and over here behind me is our aircraft in hover. At 55 decibels, this is more than 1,000 times quieter than a helicopter taking off at 90 decibels.
Compared to conventional helicopters, eVTOL aircraft aim to be quieter, cheaper and safer. Low noise, in particular, is seen as a key enabler for public acceptance and widespread adoption. But just how quiet can these eVTOL aircraft be? What progress has been made and demonstrated in this regard so far? To answer these questions, this video reviews patents on noise by Joby Aviation, noise optimizations by the wider industry, and flight test videos by Joby and Archer. Let's start with Chapter 1. How do aircraft generate noise? To answer this question, we have to understand what sound waves are. Afterward, we will look at a specific subset of sounds we call noise. Finally, we will examine the different sources of aircraft noise. First, the physical properties of sound waves. An aircraft uses atmospheric air to stay airborne and propel itself forward. In doing so, the air between the aircraft and our ears vibrates, and our hearing system perceives these pressure fluctuations in the air as sounds. To fully understand how aircraft generate noise and what eVTOL companies are doing about it, let us start from the beginning by reviewing the properties of sound waves with the following clips.
This is what a sound wave sounds like. But what does a sound wave look like? Well, the air through which the sound wave is traveling looks something like this. But if you want another visual representation of the sound, we can hook this speaker up to an oscilloscope and it gives us this graph. We say that this shape represents the sound wave because if we focus on a single molecule of air, we see that it moves back and forth just like a sine or cosine graph. The horizontal axis here represents time, and the vertical axis can be thought of as representing the displacement of that air molecule as it oscillates back and forth. If we turn up the volume, we see that the oscillations become larger and the sound becomes louder. The maximum displacement of the air molecule from its undisturbed position is called the amplitude. Another key idea is the period of a sound wave. The period is defined to be the time it takes for an air molecule to fully move back and forth one time. We call this back and forth motion a cycle. We measure the period in seconds, so the period is the number of seconds it takes for one cycle. If we decrease the period, the time it takes for the air molecules to oscillate back and forth decreases, and the note or the pitch of the sound changes. The less time it takes the air molecules to oscillate back and forth, the higher note that we perceive. An idea intimately related to the period is called the frequency. Frequency is defined to be 1 over the period. So since the period is the number of seconds per oscillation, the frequency is the number of oscillations per second. Higher notes have higher frequencies and lower notes have lower frequencies.
As the clip showed, sound waves are pressure fluctuations with an amplitude and a frequency. While we cannot see sound waves with our eyes, we can with experiments.
In this video, we're going to use our Schlieren optics setup to try to visualize sound waves traveling through the air. The transducer here is producing sound waves, and every time it produces a wave, we're going to flash a light on for just a few microseconds, and that will effectively freeze that wave in space. But you're not going to see just one wave frozen in space, because this thing produces 28,000 waves every second. So you will see a whole series of them frozen in space. So let's have a look. All right, I'm going to turn on the sound waves, the transducer. Seeing the waves move forward, we can now show you some of the characteristics that are common to all waves. Here's a piece of plastic which I'm going to use as a reflector and put it into the path of these traveling waves. And you can see the waves are reflected upward. For example, if I move the reflector in the other position, I can reflect them downward. I can reflect them downward so that they bounce off of the base of the mirror and back up again. And if I set this reflector down, you will see that the waves also bend around this barrier. They bend around and actually go into the shadow of the barrier, and this is what we call edge diffraction.
As the clip showed, sound waves propagate in patterns, and they become reflected, diffracted, and absorbed by objects they encounter. Therefore, acoustic and aircraft engineers can manipulate the sound source and its surrounding environment to control how sound waves are radiated and distributed in space, and thus perceived by our hearing system. Next, let's watch a clip of how common sounds actually look like, using the same experimental technique from the previous clip.
Here's a book landing on a table. The end of a towel being snapped. A firecracker. An AK-47. And of course, a clap.
We just examined the physical properties of sound waves. Let's move on to the next topic. What is noise, and how can we define it? Noise is a term for undesirable sounds that evoke negative psychological reactions, such as annoyance, anger, or even pain. Noise generally has two components: loudness and annoyingness. For example, loud music at a restaurant can be perceived as noisy. However, the same music can be pleasant if the sound level is lowered to the right volume. So, loudness plays a role in our perception of noise, and louder sounds are generally more likely to be noisy. However, loudness alone is sometimes not enough. For example, music at a concert can be very loud, but not perceived as noisy by its attendees. On the other hand, some sounds can be relatively quiet, but are still considered noise because of their spectral distribution or context. For example, the sounds of a person eating with their mouth open can be quiet but still perceived as noisy by other people. So, what factors contribute to perceived loudness and annoyingness? Let's now examine the contributors to noise, which has loud and annoying components. Let's start with the contributors to loudness. Loudness is the subjective perception of sounds. It is metric for ordering sounds on a scale ranging from quiet to loud, and it depends on several physical and environmental factors. Regarding physical factors, loudness depends on the sound pressure, frequency, and distance. Loudness increases with sound pressure and vice versa. Sound pressure depends on the acoustic power of a sound source, or, in other words, the rate at which some form of energy is converted into acoustic energy. The human hearing system has an upper and lower limit for sound pressure. Sounds below 20 micropascals are inaudible, and sounds above 20 pascals start to become painful. Loudness also depends on the frequency of the sound. Our hearing system can detect pressure fluctuations between 20 Hz and 20 kHz. Within this audible range, we generally find higher pitched sounds to be more annoying than low pitched ones. and we are most sensitive to sounds between 3 and 4 kHz. Here is a demonstration of sounds at a constant pressure, but at different frequencies. You should be able to perceive the different loudness. Loudness also depends on the distance. Sounds become quieter as they move away from the source. One reason is attenuation, which is the conversion of acoustic energy to heat. As air particles transfer the sound wave, they convert some acoustic energy to heat, resulting in the sound wave losing sound pressure and becoming quieter. If you stand further away from the sound source, you receive sound waves that have experienced more attenuation and have lower sound pressures. Furthermore, sound waves with higher frequencies attenuate more quickly. The other reason is that sound waves propagate and expand. As we saw in the previous clip, sound waves expand outward from their source. Therefore, the acoustic energy gets distributed over an increasingly larger area. For example, consider a spherical propagation pattern. If you double your distance from the source, the sound intensity reduces by a factor of 4. And if you triple your distance, the sound intensity reduces by a factor of 9. Loudness also depends on environmental factors. Sound waves interact with their physical environment. As we saw earlier, sound waves can be reflected, diffracted, and absorbed by objects they encounter. So, the physical environment influences how acoustic energy is distributed in space and how we perceive sounds. For example, is the aircraft flying in an environment with many sound reflective surfaces like asphalt roads and concrete walls? Or is it flying in a more sound benign environment like an open grass field that can absorb sound waves? The sound environment also plays a role in our perception of noise. Our hearing system constantly searches for sounds that stand out. For example, a person whispering at a loud party may go unnoticed, but the same person can be easily heard in a quiet exam room. So, an eVTOL aircraft may be perceived as noisy in a quiet neighborhood, but may blend in and be less noticeable in a noisy city center. We just discussed loudness, one of the two components of noise. Now, let's discuss annoyingness, specifically the contributors to annoyingness. Annoyingness depends on the sound's physical characteristics and the human context. Regarding physical characteristics, sounds can vary in loudness, pitch, duration, rhythm, and so on. Generally speaking, continuous and predictable sounds are less disruptive than intermittent and irregular sounds. Sounds can also be narrowband or broadband. Narrowband should generally be avoided because they stand out more and capture our attention more easily. For example, a police siren produces tones that grab our attention immediately. On the other hand, sounds generated by the winds or the sea are less distracting and attention-grabbing, even if they are loud, due to their broadband characteristics. The human context also determines whether the sound is disruptive or not. For example, different cultures have different expectations for their sound environment. There are varying norms and tolerances for noise. People can have different attitudes toward air travels, influencing their perception of the aircraft and, by extension, the aircraft's noise. For example, communities that regularly benefit from air travel may find the noise less irritating because they associate it with something positive. Psychological factors, such as an individual's mood, stress levels, and focus, also play a crucial role. A person trying to concentrate on a task might find aircraft noise more bothersome than in other situations. On the other hand, people at an airshow may enjoy the sounds emitted by the aircraft. In summary, noise has two components, loudness and annoyingness. Now, let's discuss the different metrics of noise. Let's start with the metrics of sound pressure. We commonly use a decibel meter with a built-in microphone to measure the sound pressure. The results are displayed in decibels or adjusted to A-weighted decibels. So, what are decibels? It is a dimensionless unit that functions like a percentage, describing a measured sound pressure in terms of a reference sound pressure. For example, a reading of 20 micropascals is converted to 0 decibels, and a reading of 20 pascals is converted to 120 decibels. But why do we use decibels? The answer has to do with our hearing system. As mentioned earlier, 20 micropascals and 20 pascals are our hearing system's lower and upper limits. We have evolved in such a way that we can tolerate well over a millionfold change in the level of pressure fluctuation. Converting pascals to decibels means changing from a linear to a logarithmic scale, thus making it easier to communicate wide-ranging pressure values. For example, 0 and 120 decibels have a much smaller range on the number line than 20 micropascals and 20 pascals. A log base of 10 was chosen to make the arithmetic of converting pascals to decibels simple. For example, multiplying 1 pascals by a factor of 3 is equivalent to adding 10 decibels. Note that this logarithmic relationship between these two units was designed for convenience and is not based on physics. This point is important to remember for the later section of this video, so I repeat. The logarithmic function for converting pascals to decibels is for convenience and has no psychoacoustics basis. So, we just covered the metrics and units of sound pressure, which are sometimes used as a proxy for loudness and noise. Next, let's discuss actual metrics of loudness. As mentioned earlier, loudness depends on the sound pressure and the frequency. A-weighting is an empirical correction factor that captures this frequency dependency. Here's how it works. First, a standard frequency of 1 kHz is selected, which is the reference frequency against which all other frequencies are compared. Then, sounds at other frequencies have their decibel values adjusted to reflect their equivalent loudness at 1 kHz. For example, a sound at 100 Hz and 59 decibels would be as loud as a sound at 1 kHz and 40 decibels. Phon is another unit of loudness and is generally more accurate than A-weighted decibels. The A-weighting curve we saw earlier is based on the 40 phon equal loudness contour of the Fletcher-Munson curves. To create these curves, a group of people invited to experiments where they were asked to evaluate the loudness of different sounds. In this way, scientists were able to capture the frequency dependency of loudness. Finally, let's discuss the unit son. Sons were invented with the help of empirical data to measure loudness on a linear scale, making it more intuitive to use. For example, doubling a sound's sons equals doubling its loudness. Contrast this with pascals and decibels, where doubling a sound's pascals or decibels does not equal doubling its loudness. Finally, as this graph shows, the relationship between sound pressure and loudness is non-linear, because our hearing system has evolved to be more sensitive to lower sound pressures. So, here are 2 rules of thumb. First, doubling the frequency corresponds to adding 10 decibels to the sound pressure level and doubling the loudness. This rule works up to 3000 Hz. Second, multiplying the sound pressure by a factor of 3 corresponds to doubling the loudness. This rule applies to sounds at the standard frequency of 1000 Hz. We just covered one component of noise. Let's briefly cover the other component, annoyingness. Annoyingness depends on the sound's duration, tonal content, and context. The metrics sound exposure level and effective perceived noise level are based on A-weighted decibels and consider a sound's annoyingness to measure noise more accurately. Sound exposure level builds upon the A-weighted decibels and considers the sound's duration. As the graph shows, the sound exposure level represents all the acoustic energy measured over an event as if the duration of the event was just 1 second. In this way, the sound exposure level captures the duration of the noise, allowing sounds of different durations to be compared. Effective perceived noise level builds upon the sound exposure level and considers the tonal content. It penalizes tones, aiming to capture the human's sensitivity to tonal noise. The effective perceived noise level is one of the most accurate ways to measure noise and is used in aircraft noise certification. Let's move on to the next topic, which is the sources of aircraft noise. Let's begin by discussing the noise taxonomy. The noise taxonomy is a classification system that helps us organize the different noise sources. For example, aircraft noise can be classified with these 3 attributes: the responsible aircraft component, the responsible mechanism, and the resulting spectral characteristics. After the noise sources have been categorized by the attributes, they can then be broken down into greater detail and ordered in a hierarchy. Aircraft noise can be classified by the responsible components. The main noise sources are usually the rotors, propellers, and engines. Some noise contributions come from the airframe and landing gear. Aircraft noise can also be classified by the responsible mechanisms, which have a mechanical or aerodynamic origin. Most aircraft noise sources have an aerodynamic origin. The aircraft components we saw earlier generate noise via different mechanisms. For example, an airfoil generates sounds with the aerodynamic mechanisms illustrated on this slide. Many mechanisms are common to all types of aircraft, while others are specific. Finally, sounds generated by these mechanisms can have different spectral characteristics. For example, they can be tonal or broadband, high frequency or low frequency. An aircraft's spectral characteristics play a crucial role in our perception of loudness and noise, so it's important to distinguish the different noise sources by their contributions to the overall sound profile. We just covered 3 attributes that are commonly used for noise classification. Other attributes can be considered to improve the discussion in specific contexts. For example, noise can also be classified by the sound wave's directivity, or whether it can be determined analytically. However, we will not use these attributes for our discussion today. By convention, we classify the noise sources as follows. We first classify them by the responsible aircraft components, then by the spectral characteristics, and finally by the responsible mechanism. This hierarchy helps us break down the complexity of aircraft noise and obtain deeper insights into their mechanisms. Let's look at 2 examples to see how this classification system works. The propeller is the dominant noise source for an airplane, so it is broken down and analyzed as shown. For a helicopter, the main rotor and the tail rotor are the dominant noise sources, making them the focal points of acoustics optimizations. Using this classification system, let's examine the different mechanisms for airplane noise. For subsonic aircraft, the main noise sources are the propellers and the engines. The airframe and the landing gear are noise contributors, but are generally less noticeable in the presence of a spinning propeller. Hence, for scoping reasons, we will only examine propeller noise today. The propeller generates noise with both tonal and broadband characteristics. Let's examine the mechanisms for these different characteristics. Tonal noise is generated by two mechanisms, blade thickness and blade loading. First, as a propeller blade cuts through the air, it forces air to be moved onto its upper and lower surfaces. This air displacement creates pressure fluctuations in the air and, therefore, sound waves and noise. Second, as the air moves along the airfoil, it generates a pressure field and aerodynamic loads like thrust and drag. These aerodynamic loads also result in pressure fluctuations and noise. But why do air displacements and aerodynamic loads create pressure fluctuations? Since a propeller spins about an axis, the air displacement and aerodynamic loads we just mentioned are based on a rotating frame. Hence, from a stationary point of view, these air displacements and aerodynamic loads occur in an oscillatory manner. For example, the propeller blade causes air to compress in 1/2 of a revolution, but causes air to then decompress in the other half of the revolution. The same compression and decompressions are then repeated in the next revolution, resulting in pressure fluctuations. These pressure fluctuations occur at a frequency that is equivalent to the propeller's rotational speed. The frequency of tonal noise depends on the frequency at which propeller blades pass a fixed point, the blade passage frequency. In other words, the frequency equals the number of revolutions per second multiplied by the number of propeller blades. If the number of revolutions per second increases, the sound wave's frequency and pitch also increase. This is why, for example, your washing machine has a lower pitch when spinning slowly, but a higher pitch when spinning faster. Regarding the blade count, if the number of propeller blades increases, the sound wave's frequency and pitch also increase. For example, if the blade count is doubled from 2 to 4 and the rotational speed is held constant, then the blade passage frequency doubles and the tonal noise increases by an octave in pitch. Next, let's discuss broadband noise. Broadband noise results from random pressure fluctuations on the blade surface. It is typically more dominant at higher frequencies where the tonal components have decayed. These random pressure fluctuations are generated by the blade itself or induced by an external source, such as winds or the turbulent wake of another propeller. There are at least 4 mechanisms for the blade to generate noise by itself. As the picture illustrates, self-noise can be due to turbulence on the trailing edge, turbulence from flow separation or stall, vortex shedding on the trailing edge, and vortex formation on the blade tips. These mechanisms cause random pressure fluctuations in the air and thus produce sounds of different frequencies, which is a typical characteristic of broadband noise. Then there is turbulent ingestion noise. This category includes, for example, blade-wake interaction noise and atmospheric turbulence interaction noise. As the names imply, blade-wake interaction noise results from a blade passing through the wake of a preceding blade or the wake of a preceding propeller. And atmospheric turbulence interaction noise is due to the propeller interacting with turbulent winds. Okay, we just covered airplane noise. Next, let's talk about helicopter noise. For a helicopter, the major noise sources are the main rotor, the tail rotor, and the engine. For scoping reasons, we will only examine the main rotor today. Rotor noise can also be divided into tonal and broadband components, just like before with propeller noise. Then, the tonal components can be attributed to the rotor blade thickness and aerodynamic loading, as was the case for propeller noise. However, a key difference between rotors and propellers is that a rotor can have high-speed impulsive noise. High-speed impulsive noise is generated when the rotor blades, typically on the advancing side, reach transonic or supersonic speeds. Compressibility effects become significant as the blade's relative airspeed approaches the speed of sound, leading to shock waves and sonic booms. Helicopters have rotors operating in edgewise flow, so the relative airspeed at the advancing blade is the sum of the flight speed and tip speed. In contrast, airplanes have propellers operating in axial flow, so there are no advancing and retreating blades, and the relative airspeeds at the blades are mostly uniform. Therefore, airplanes do not have high-speed impulsive noise. Another key difference between rotors and propellers is that rotors can have blade vortex interaction noise, otherwise known as blade slaps. Blade vortex interactions are usually the noisiest mechanism, as they can result in very loud sounds. They result from a rotor blade interacting with the tip vortex of a preceding blade. This interaction leads to impulse-like loading at the rotor's leading edge. Consequently, this noise appears as sharp impulses on a sound spectrum. Here is a demonstration of blade slaps. First, this is what tip vortices look like. This is what blade vortex interactions look like.
So I'll show you guys what blade slap is here. Blade slap occurs if you're at a high rate of speed and a low collective setting. So I'm going over the top of Mark Johnson's house here. We'll throw a little blade slap in there to wake him up here. Hey, you guys hear that? That's blade slap. If I go farther down, it goes away. If I come back up like that, it goes away.
In summary, here are the key points for how aircraft generate noise. First, noise is an undesirable sound and a subjective metric. Noise is a function of loudness and annoyingness, and sound pressure can be used as a basic proxy for noise measurements. More accurate noise metrics use empirical data to capture the human's subjective response to different sounds. Aircraft certification requires accurate noise metrics like the sound exposure level or the effective perceived noise level. An aircraft has numerous noise sources. The most dominant ones are from the propellers and rotors. Propellers and rotors share many noise characteristics and mechanisms. A key difference is that rotors can have additional high-speed impulsive noise and blade vortex interaction noise, since they operate in edgewise flow, whereas propellers operate in axial flow. Chapter 2. How can eVTOL aircraft reduce noise? Let's first discuss noise reduction strategies at the blade level. Blade tip speed. The objective is to minimize blade noise. One strategy is to reduce the loudness of the blade noise by lowering the sound pressure. The sound pressure is reduced by lowering the blade's dynamic pressure, which is achieved by lowering its speed. However, other engineering constraints, such as physical space and weight, limit the extent to which the blade speed can be lowered. As this equation shows, the dynamic pressure is a function of the speed squared. So, on the one hand, we want to lower blade tip speeds to achieve lower dynamic pressure. But, on the other hand, we are constrained, because lower dynamic pressure means we must increase the blade area to maintain the thrust requirement. New technologies and innovation can move conventional design constraints. For example, Joby's propeller blades are made of carbon fiber and titanium, which use their low mass densities to enable large propellers and lower blade tip speeds.
So here's one of the propulsion blades. And so it's carbon fiber with a titanium root sleeve. This combined with the very high specific torque motor is what makes the acoustic profile possible.
Airfoil shape. In addition to the tip speed, the blade geometry contributes to the flow characteristics and noise. For example, the airfoil shape determines where the flow separates from the surface at different angles of attack. Therefore, the airfoil shape influences separated flow noise, otherwise known as stall noise. Electric vertical takeoff and landing brings new design challenges and approaches for airfoil shapes. For example, Joby's airfoil has an unconventional bump to achieve numerous aeroacoustics benefits. The first benefit is that Joby's airfoil enables the propeller blade to be more evenly loaded than a conventional airfoil when operating under asymmetrical inflow conditions. When the eVTOL aircraft is flying, its rotor blades can meet random air turbulence. This turbulence means that the airflow across the rotor blade varies in speed and direction, so the blade sections experience different effective angles of attack. As a result, the blade sections generate different levels of lift and drag, creating pressure fluctuations in the air and thus noise. The figure on the bottom right compares Joby's airfoil against a conventional airfoil. As we can see, Joby's airfoil has a shallower slope, so it is less sensitive to changes in angles of attack. This means that Joby's airfoil is not as strongly affected by random turbulence as the conventional airfoil, because its blade sections generate a more uniform pressure distribution. The second benefit is that Joby's airfoil enables more gentle stall behavior and possibly reduces noise from flow separation. These two figures show that Joby's airfoil keeps the flow separation point localized near its unique bump, reducing the drag influence of flow separation and delaying the onset of aerodynamic stall. Thus, Joby achieves a wider operable range of angles of attack, making its stall behavior more gentle. Like the first benefit, this airfoil behavior makes the propeller blades less sensitive to varying inflow conditions. Other important blade parameters include the taper ratio, the twist rate, and the aspect ratio. These three parameters can be varied to optimize the blade loading distribution, tip losses, and noise. For example, a higher taper ratio and a higher aspect ratio minimize the pressure losses and tip vortices at the blade tip. Thus, like other aerospace companies, Joby uses acoustics modeling, simulations, and experiments to optimize these blade parameters for noise. Tip shape. Another option for reducing tip losses is the tip shape, such as these anhedral tips by Joby and Archer. Next, let's compare eVTOL aircraft to conventional aircraft at the blade level. Aeroacoustics optimization at the blade level can also be conducted for all other aircraft types, including conventional helicopters. For example, Eurocopter's blue edge blades use a unique geometry to lower noise. So, electric vertical takeoff and landing does not bring an inherent aeroacoustic advantage at the blade level. Next, let's talk about noise reduction strategies at the rotor or propeller level. First, rotor solidity. The objective is to minimize rotor noise. A rotor consists of rotor blades, so one strategy is to reduce the sound pressure by lowering the blade loading. The blade loading can be lowered by decreasing the disc loading or increasing the rotor solidity. Since eVTOL aircraft have much higher disc loadings than conventional helicopters, they must use higher rotor solidities to achieve low noise. However, higher rotor solidities have several downsides, including greater rotor weight, greater motor weight, and lower efficiency. As these pictures show, Joby's aircraft have higher rotor solidities than comparable helicopters. As discussed, this is because the blade loading must be low to minimize pressure fluctuations and sound pressure. But at the same time, electric vertical takeoff and landing results in high disc loadings. Joby mitigates the downsides of high rotor solidity with a propeller made of carbon fiber and titanium and an electric motor with a very high specific torque. Blade passage frequency. As discussed in Chapter 1, the blade passage frequency determines the pitch of the sound waves. One way to reduce noise is to increase the frequency so the sound waves become ultrasonic and inaudible to humans. The following clip demonstrates the potential of this noise reduction strategy.
Most engines are very loud. For now, I mean, why don't you tell us, like, just super high level, what are the things that can keep an engine like yours both efficient but also quiet?
Yeah, so the trick that we do is we take all of the sources of noise, we minimize them, and then we push the tones that you would typically hear, which is the blade passage frequency, up into the ultrasonic. Blade passage frequency, it's a function of the rotations per second and the number of blades that you have. You know, most fans, open rotors, propellers, ducted fans, they have 2, 5, maybe 20 blades. And they're spinning at like a reasonable RPM or rotation per second that puts that frequency right in human hearing. So to get it into the ultrasonic, it has to spin faster. But there's problems with taking the same fan and spinning faster. There's contributions to the noise that go with the fifth power of the tip speed. And if you imagine that, you know, tip speed is a huge contributor and it's a function of your rotations per second, you can't just spin faster to get to lower noise. So our trick has been, we've developed this high blade count fan that you can actually rotate at a reasonable rotation per second. That still puts the blade passage frequency up into the ultrasonic and allows us to do really clean and efficient work as it spins.
So, how many blades does Whisper Aero have? We can make an estimate using publicly available numbers. Our first assumption is that the blade passage frequency must be greater than 20,000 Hz for the sound to be ultrasonic. Our second input is from the video. Whisper Aero has stated that their blade tip speed has a Mach number of less than 0.3. Finally, we know from publicly available information that their duct diameter is 4 to 24 inches, so the blade length is around 5 to 30 centimeters. Using this information, we can estimate the blade count to be around 62 for the small ducts and around 372 for the large ducts. Whisper Aero creates propulsors for conventional takeoff and landing. The question is, could ultrasonic blade passage frequencies be viable for vertical takeoff and landing? As this table shows, the answer is no. This idea seems impossible for open rotors because their frequencies are off by several orders of magnitude. Though this idea could be made possible for small ducted fans, as shown by Lilium's blade passage frequency of 4000 Hz, ducted fans are generally too inefficient for vertical takeoff and landing. There is another idea related to the blade passage frequency. The other noise reduction strategy is to distribute the blade passage frequency. For example, Joby's blades are spaced unevenly, creating more varied blade passage frequencies and lowering the peak amplitude at any particular frequency. As a result, Joby lowers the peak acoustic power and therefore lowers the perception of loudness and noise. To illustrate this idea, let us compare two images. The first image is a computer-generated image of Vertical Aerospace's aircraft. As you can see, the propeller blades fit perfectly inside a regular pentagon, so the blades are spaced evenly apart. Contrast this with the second image, which is a real photograph of Joby's prototype. As you can see, the propeller blades cannot be aligned with a regular pentagon. In other words, they are spaced unevenly and thus achieve the noise reduction effect we reviewed moments ago. Here is a close-up view. Ducts with acoustic liners. Ducts encase the rotor, fan or propeller and reduce noise by absorbing some of the acoustic energy. Acoustic liners on the inner walls of the duct improve sound absorption further, and they can be designed to target specific frequencies to become even more effective. However, ducts do not scale well with rotor diameter due to increasing larger excessive weight and drag. Therefore, ducts must be kept small in diameter and, as a result, are not a viable noise mitigation strategy for eVTOL aircraft. Next, let's compare eVTOL aircraft to conventional aircraft at the rotor level. Aeroacoustics optimization at the rotor level can also be done for conventional aircraft. For example, Airbus's H160 has a duct tail rotor instead of an open tail rotor. Furthermore, Airbus helicopters also uses unevenly spaced blades. As the picture shows, the helicopter's tail rotor has non-equally spaced blades, which distribute the blade tones over a greater frequency range and thus reduce the acoustic intensity. So, eVTOL aircraft do not bring an inherent aeroacoustics advantage at the rotor level. Okay, we just talked about isolated rotor designs and operation. Now, let's talk about noise reduction strategies at the aircraft level. Aircraft configuration. The objective is to lower aircraft level noise. One strategy is to optimize the aircraft configuration for aeroacoustics. For example, the following strategies can be considered to avoid rotor-airframe interaction noise: increasing the separation distances between the rotor and the airframe, and avoiding pusher propeller configurations that are near a fuselage, rotor wake, or wing wake. Aircraft level blade control. A particularly important aeroacoustics interaction is the blade vortex interaction, because it is a very large noise contributor for rotorcraft. Winged eVTOL aircraft can also have blade vortex interactions, since their propellers are in edgewise flow during thrust-borne flight. For example, these pictures show that Joby's aircraft can still have blade vortex interactions at certain flight speeds and descent rates. Helicopters avoid blade vortex interactions by controlling their flight speeds and descent rates. eVTOL aircraft have the potential for even better control. Joby, for example, avoids blade vortex interactions by controlling each individual propeller's tilt angle, rotational speed, and blade pitch. Unfortunately, Joby's website does not detail any specific information about this control method. In any case, this method would only be feasible for eVTOL aircraft with distributed electric propulsion. If this method is effective, it can be very valuable in reducing noise during the eVTOL aircraft's transition phases. Another strategy is controlling the rotor-rotor aeroacoustics interactions. Aeroacoustics interactions between two or more rotors can be minimized by adjusting the rotor phases. Depending on the strategy, noise can be reduced via a reduction in radiation efficiency or through superposition. Both strategies require precise rotor azimuth positions relative to other rotors. Electric motors enable more accurate azimuth position control, making this noise reduction strategy more viable. Another strategy is to control the propeller's frequency distribution. For example, Joby controls the blade passage frequency of every propeller, making every propeller emit a slightly different pitch and spreading the acoustic power over a greater frequency range. This frequency control is achieved by a control feedback loop at every propeller. The control loop uses a microphone to measure the tonal noise emitted by the propeller. It then manipulates the rotational speed and thus controls the blade passage frequency. The control loop then adjusts the propeller blade pitch to compensate for the thrust changes made by the rotational speed. Another example of the strategy is Archer Aviation. The following video from earlier this year shows that the Archer Midnight aircraft flies with the propellers spinning at different speeds. Is Archer also using the strategy to reduce noise? Electric propulsion system. We will not cover this topic in detail. In short, if you exclude aerodynamic noise, electric propulsion is quieter than combustion-based propulsion since it has fewer mechanical mechanisms. Next, let's compare eVTOL aircraft to conventional aircraft at the aircraft level. Evidently, conventional and eVTOL aircraft have significantly different configurations and propulsion systems, which are the reasons for the aeroacoustics differences. Many of the noise reduction strategies at the aircraft level are exclusive to distributed electric propulsion. However, there are downsides too. As we discussed earlier, eVTOL aircraft have multiple rotors, so they have more rotor-rotor and rotor-airframe interactions. Many eVTOL aircraft are designed from scratch, so their manufacturers can use modern aeroacoustic simulations powered by state-of-the-art hardware and software to optimize their eVTOL aircraft for noise from scratch. Traditional companies are not as well positioned as startups to adopt these new aeroacoustic simulation tools in their design processes. Okay, let's now talk about noise reduction strategies at the airline level. Flight plan and operations. We will not cover this topic in detail. In short, the objective is to minimize noise at an airline operation level. The eVTOL aircraft can be operated in ways that minimize disturbance on the ground. For example, the eVTOL aircraft can be flown at higher altitudes and away from people to reduce noise. However, this can come at the cost of transportation efficiency because the eVTOL aircraft may need to take a longer route. Let's briefly compare eVTOL aircraft to conventional aircraft at the airline level. The same noise regulations and limits that apply to conventional aircraft would also apply to eVTOL aircraft. Hence, for a given noise budget, if the aircraft is quieter, more of them can be used. For example, if Joby's aircraft could be as quiet as shown in this simulation, it could fly new routes without disturbing people, or fly existing routes in greater volume, assuming noise was the limiting factor. In summary, here are the key points of Chapter 2. There are various strategies for reducing noise. Blade, rotor, and airline level strategies can be applied to both eVTOL aircraft and conventional aircraft. The differences are at the aircraft level due to distributed electric propulsion. For example, eVTOL aircraft can control their rotors to avoid blade vortex interactions. They can also spin their rotors at different speeds to spread the acoustic energy across more frequencies and reduce tones. Many eVTOL aircraft are designed from scratch, hence companies can use modern aeroacoustic simulations powered by state-of-the-art hardware and software to optimize their eVTOL aircraft for noise from scratch. eVTOL companies can also use more advanced noise metrics to optimize their eVTOL aircraft. Traditional companies are not as well positioned as startups to adopt these new aeroacoustic simulation tools in their design process. Chapter 3. What is possible for eVTOL noise? And what is hype? Is it possible for eVTOL aircraft to be 100 times quieter than a helicopter? Archer and Joby have similar claims regarding noise. For example, Archer claims, "At takeoff and landing, we designed the aircraft to be 10 times quieter than a helicopter. And during cruise flight 2,000 feet above cities, we designed the aircraft to be 100 times quieter." Similarly, a blog article on Archer's website states, "The design of Maker is such that the noise that reaches the ground should measure around 45 A-weighted decibels, almost 100 times quieter than that of a helicopter." Another blog article says, "Helicopters produce 78 decibels of sound at a cruising altitude of 2,000 feet. So a helicopter is actually about 1,000 times louder than our eVTOL aircraft." Joby made some similar statements. For example, this news article on Joby's website states, "Our aircraft emits 100 times less noise than a traditional helicopter." A written testimony of Joby's CEO says, "Our airplane measures 65 A-weighted decibels during takeoff and landing, and 40 A-weighted decibels in overflight. This is roughly 100 times less acoustic energy than a traditional rotorcraft." There are problems with these claims. These claims are based on A-weighted sound pressure level. The reasoning is if the sound pressure drops by 20 to 30 A-weighted decibels, the sound becomes 100 to 1,000 times less powerful, and therefore 100 to 1,000 times quieter. However, as explained in Chapter 1, if a sound is 100 times less powerful, it does not become 100 times quieter, because loudness does not scale linearly with pressure, nor does loudness scale linearly with the sound intensity. So, what's the actual change in loudness? If we use Archer's and Joby's assumptions and recalculate with the necessary corrections, we find that an eVTOL aircraft would be approximately 4 to 8 times quieter than a helicopter. However, I repeat, these numbers are all based on Archer's and Joby's assumptions. So, let's go back to the statements by Archer and Joby. Here, the use of 100 times quieter is incorrect. In contrast, 1,000 times more powerful accurately describes sound intensity. The use of 1,000 times louder than our eVTOL aircraft is certainly incorrect. The use of emits 100 times less noise is questionable and unlikely, since the loudness only differs by 1 order of magnitude or less, and the tonal qualities cannot make up for the remaining order of magnitude. 100 times less acoustic energy is an accurate description. In summary, it seems that Archer and Joby may have, at times, misunderstood or misrepresented the concepts of loudness, decibels, and sound intensity. Using their assumptions, their aircraft would not be 100 to 1,000 times quieter than a helicopter, but only 4 to 8 times quieter. Review of Archer and Joby. Hoverflight noise. How do Archer's claim compare to independent measurements? Archer stated that its aircraft would be 10 times quieter than a helicopter during takeoff and landing. Though Archer gave no official values for the sound pressure level or effective perceived noise level, we can safely assume that a 10-fold loudness reduction is impossible. We can get a more realistic estimate of Archer's status by using data from other industry observers and analysts. For example, the YouTuber eVTOL Research posted a video on Archer and Joby. In this video, they traveled to Salinas Airport and recorded and measured Archer's midnight aircraft. They measured an audio level of 74.8 decibels at a distance of 85 meters. If we extrapolate the YouTuber's data, we find that Archer's midnight aircraft would have around 73 decibels at 100 meters. Compared to a helicopter at 80 to 90 decibels, Archer's aircraft would be roughly 2 to 4 times quieter. Interestingly, if we calculate the sound pressure inside the aircraft, we find a sound pressure level of 93 decibels at 10 meters. At this level, I imagine hearing protection would be mandatory for passengers and pilots. Next, let's examine Joby. How do Joby's measurements compare to independent ones? In one of Joby's YouTube videos, they measured an audio level of 54.5 decibels at a 100-meter distance from their aircraft. In comparison, the YouTuber eVTOL Research got a value of 68.6 decibels at a distance of 37 meters. Like before, if we extrapolate the YouTuber's data, we find that Joby's prototype would have 60 decibels at 100 meters. So, our extrapolated value of 60 decibels is higher than Joby's measured value of 54.5 decibels. On Joby's website and in Joby's written testimony to the US Congress, Joby states that the airplane measures 65 decibels during takeoff and landing from a distance of 100 meters. In this case, our extrapolated value of 60 decibels would be lower than Joby's estimate. If we calculate the sound pressure inside the aircraft, we find a sound pressure level of 80 decibels at 10 meters. At this level, I imagine hearing protection could be unnecessary, but still recommendable for passengers. Cruise flight noise. Archer claims that its aircraft will be 45 decibels when cruising at 2,000 feet, or 610 meters. If we look at the YouTuber's recording, we find that at this timestamp, the measured sound pressure level was 45.2 decibels. However, the YouTuber did not mention or measure the distance from the aircraft at this point, so it is unclear whether Archer's claim has been achieved. Meanwhile, Joby claims that its aircraft will be 45 decibels when cruising at 1,640 feet, or 500 meters. This means that Joby's target is even more ambitious than Archer's, since the same 45 decibels must be achieved at a closer distance. Like before, the YouTuber did not measure the distance from the aircraft, so it is unclear whether Joby's claim has been achieved. I should mention the flaws in the YouTuber's measurements, because they must be considered when drawing conclusions. The flaws are: the aircraft's weight is unknown. It is unclear if Archer and Joby flew at full payload. If these test flights were conducted without payload, the aircraft can operate at a lower throttle and should be quieter. Second, the acoustics environment was not controlled. As discussed, the acoustics environment influences sound measurements. As we can see from the pictures, the environment of the two aircraft was very different. Archer was flying over an open grass field, whereas Joby was flying over a concrete floor. Third, it was only a single measurement, so there were no repetitions. And fourth, the measurement method was very simple, as seen from the pictures. There was no microphone array or things like that. Nonetheless, these measurements are the best we have at the moment, at least in the publicly available space. So it is still useful to draw conclusions as long as we are mindful of its flaws. On the 2nd of August 2021, Joby demonstrated the low noise level of its cruise flight. In a YouTube video, Joby showed how its aircraft is significantly quieter than comparable conventional aircraft. As we can see from this graph, Joby's aircraft has by far the lowest amplitude, so its sounds are the quietest. Furthermore, Joby's sounds are much more broadband and have fewer tonal components. So Joby's aircraft sounds are less annoying and overall less noisy. Next, let's watch Joby's YouTube video using the knowledge we have learned so far. eVTOL noise, What's possible? What's hype? Let's summarize the key findings of this video to answer this question. As discussed in Chapter 1, noise is an undesirable sound that depends on sound pressure, frequency, tonal content, and duration. Loudness and sound pressure are sometimes used as proxies for noise. This knowledge is important for understanding and evaluating the claims of various eVTOL companies. For example, Archer and Joby have claimed in the past that their aircraft is or will be 100 times quieter than a helicopter. However, such claims are based on the false premise that loudness scales linearly with sound intensity. As Chapter 1 explained, loudness scales progressively less with sound intensities. In fact, using the eVTOL manufacturer's assumptions, their aircraft is only 2 to 4 times quieter during hoverflight and only 4 to 8 times quieter during cruise flight. Distributed electric propulsion has acoustics benefits and drawbacks. On the one hand, it enables greater rotor control, creating opportunities to minimize aeroacoustics interactions via rotor phasing and spread the acoustic power of a wider frequency range via rotational speed control. However, there are downsides to distributed electric propulsion too. As another aeroacoustics expert writes, with many rotors, propellers, and fixed aerodynamic surfaces, there's a strong possibility of unsteady aerodynamic interactions between these components, which can lead to noise generation. In terms of electric vertical takeoff and landing, there are acoustics benefits too. For example, one benefit is that Joby's eVTOL aircraft will only use a fraction of its available power and thrust for cruise flights. Or, looking at this from a different perspective, Joby's aircraft uses a much larger rotor disk area than conventional airplanes for cruise flights. This means that Joby's aircraft will operate with very low blade tip speeds and with very low blade loading, resulting in very low sound pressures. This is a clear benefit that helps reduce noise drastically. However, the aeroacoustics downsides of electric vertical takeoff and landing can be felt at hoverflights. Since eVTOL aircraft have high disk loadings, they are inherently in a worse position to achieve low noise. Consequently, eVTOL manufacturers like Joby must increase their rotor solidity to achieve their requirements for low noise. We just discussed aeroacoustics from a theoretical point of view. What about in practice? As we saw from real flight tests, eVTOL aircraft are mostly comparable to conventional helicopters in terms of noise during takeoff and landing. Some eVTOL aircraft may be 2 to 4 times quieter. In terms of noise, some eVTOL aircraft can be a lot less annoying than helicopters due to less tonal and more broadband noise. For cruise flights, some eVTOL aircraft are claimed to be as quiet as 45 A-weighted decibels when flying from a distance of 500 meters. Initial flight test results indicate that 45 A-weighted decibels is indeed possible. For example, these screenshots show how Archer and Joby have achieved around 45 A-weighted decibels during their flight tests. However, since the distance in these pictures are unknown and can only be approximated by the eye, the noise claim is yet to be confirmed with more sophisticated and reliable experiments. eVTOL aircraft have the potential to be much quieter than conventional aircraft, especially for the cruise phase. Innovation is required at all system levels to achieve this acoustics potential. Innovations like the ones reviewed in this presentation can separate great eVTOL aircraft from the rest. However, these innovations also increase cost, engineering penalties, and risks. The future will tell us if such a strong focus on noise optimization, like the ones made by Joby Aviation, will pay off.